Let's review some of the concepts of vector calculus using an example. Let's suppose for this particular problem, we have uh, the following description. Okay, you may want to pause and take notes of this particular problem. You can write this example. So first of all, what's a steady, incompressible, two-dimensional velocity is given in the problem? Uh, so for this particular description given in the problem, we know that the velocity is actually equal to zero point 0.5 plus 0.8x I plus 1.5 minus 0.8 y times j. Okay, so the first thing that we want to do in this problem is we want to find the stagnation point. Now, stagnation point, a stagnation point is a point in the flow field. Remember we talked about flow fields. This is a velocity field. Okay, so stagnation point is a location. It is a point where your velocity will actually equal to 0. Okay, to set the velocity 0, the way we do the problem is we set each one of the components of the velocity, u and v. Okay, we set the components of the velocity equal to 0, and then we solve that system of equations. So we say this is 0.5, 0.8x, and we set that to 0. We say v is equal to 1.5 minus 0.8 times y set to 0. We got two system of equations, two unknowns. They are uncoupled, so we can easily find that at x equal to minus 0.625 meters and at y equal to 1.875, your velocity is stagnated because you're saying that your velocity vector is 0, 0. And you may want to, in general, it's a three-dimensional, so you saw three zeros, although you don't have them. So you're saying this is a stagnation point, okay? This is the stagnation point, and will occur only when these are equal to minus 0.625 and 1.75. Okay, so what would happen in my problem if I told you, now what happens in the problem if y is equal to 2 and x is equal to 2 and y is equal to 3? Okay, so if I calculated this, you can find that if you evaluate this, if you take this equation right here, let's keep this equation handy. It's not equal to 0 anymore. And now we replace these values, we replace these values for 2 and this value for 3. You can show that the values that you get is 2.10 and your v becomes minus 0.90. This is meters seconds, this is meters second. And now what this is really telling you is if you were to plot this this particular field and you were trying to see what happens in the region that we are talking about here, we are talking about this particular region where this is 2 and your y and the location of your y is 3. So we are talking 2 and 3. We are talking about a velocity vector here. And you can see that your velocity vector is actually going in the negative direction, right? It's pointing in this direction, it's pointing in this direction, and it's pointing in this direction because when you calculate your velocity, you realize this is minus 0.9. you realize this is moving at 2.10 meters per second. So therefore, this is how your stream field looks like at that particular point. Now, what if we wanted to find the magnitude of this vector? Okay, so at this same point, at this particular point, well, then your vector at that location is actually equal to 2.10 plus minus 0.9 j. We are working on a plane. So with that said, what we can show is if I want to find the magnitude of this vector, as we recall, we basically square each one of the components squared, and then we take the square root of that. Okay, so if you find the square root of that, you can show this is 2.28 meters per second. Okay, so now we could go ahead and find what the field looks like at each one of those points. You see, that's how we draw this vector field. We draw these fields by evaluating this at each one of those points. So in the previous example that we saw, we found this as minus 0.60 minus 0.625 and 1.85, and you can see that what happens at that particular location is this location right here. Is this location right there. That is your stagnation location. Okay, it's the location where your flow, when it moves, the velocity just becomes equal to 0. Okay, so this is one case. Now let's suppose I wanted to know what is your vector across a location right here, and I told you R is equal to I minus J. I give you the position vector, and I'm asking you to tell me what is the velocity in that particular direction. Okay, so if you remember, and this is a good example. I am really trying to do this. This is my velocity vector, and I'm saying, give me what happens to my velocity. Okay. But I want the velocity, the magnitude of the speed, and the velocity in this direction. So I want this. But I don't want only the magnitude. I also want I would like to know what is the vector that actually moves along that line. So what I'm really asking you is to find this particular vector here. I'm really asking you to find this vector here, okay? So the first step in this problem is we can do a dot product, because the dot product will give me this magnitude. Only the magnitude will give me a scalar. So I can take V dot R will give me this projection of V over R, and this vector field, if I do the dot product at that same point, okay, at the same, let's suppose we're at the same location, that would give me equal to 2.10 minus 0.9, and I'm going to do a dot product of 1 and minus 1. So when I do the dot product, you basically are multiplying each one of them individually. This is 1.1 times 1, this times this, plus this times this, 0.9, negative 1. And so this becomes 2.10 plus 0.9 is equal to 3.0 meters second. So this is the magnitude. Okay, you're only getting the magnitude in this direction. Now, if I want the vector I need to find the unit vector in this direction and multiply by the magnitude. How do I find the unit vector of ER? Well, if I want to find the unit vector, then I have to take the magnitude of that. Okay, so the vector was I minus j. Okay, and I'm going to divide this by the square root of 1 squared plus minus 1 squared. And that would give you 1 over square root of 2i minus j, 1 over square root of 2j. So this is the unit vector across along this line. So that means that the vector that I'm looking for, okay, the vector that I am looking for in the r direction will be this magnitude VR, okay, will be this magnitude VR times ER that will make it a vector. So that means that what I am saying is you're going to multiply, let's go on to the next page. I am saying you want to do vector, okay, and that is VR times ER, and so this is equal to, the magnitude was 3.0, and the vector was 1 over square root of 2i minus 1 over square root of 2j, and this whole thing gives you 2.12i minus 2.12j. So this will be the magnitude of the vector in this particular direction. Okay. Now, for this particular problem, let's suppose we have another vector in a different location and we want to find the cross product. Okay. Suppose I want to know what would be the cross product of this vector and this vector, just for the sake of this practice. So if I did that, what you can show is that if I wanted R cross product B, okay, then you write I, J, K. Your R is equal to 1 minus 1, and your B in the R direction, sorry, will be 2.12 minus 2.12, and we don't have nothing in the K. So if I take, I put this plus, minus, plus. If I take this plus and I eliminate this row and this column and this row, 0 times 0 is 0, so it's 0 I. If I eliminated this, this is a minus j, and that goes 0 times 0 is also 0. I'm only left with one component, is this, and that gives you minus 2.12 minus 2.12. Okay, minus minus becomes plus, so this is equal to 0. Okay, and actually, if I ask you what is the consequence if this equaling this being equal to 0? Does this actually make sense or it does not make sense? Well, you have to know that it does make sense, because I told you that if this is 0, what this is really saying is that my r is parallel to my velocity. And if you go back in our derivation, I just told you find the projection of v along the r direction, okay, along this vector. And that vector is actually parallel to r. So it made sense that actually I will definitely indeed get this equal to 0. Okay, so this is a small review on how your vectors work, and how all the, everything, how we bring all these topics together. This is example number one.